So this research paper just came out and it super caught my eye. Selective attention improves transformer, put out by Google Research. And up front, I think it's important to note, as far as I'm aware, not a single person that wrote the attention is all you need paper is still within Google. And then that paper is the Vaswani paper. So all throughout this, you'll notice that it references Vaswani et al. 2017. That's attention is all you need. And then so this paper builds on that paper, obviously. And then, but so I think it's interesting that this comes out from Google. And then so the paper is 22 pages long and it's very in depth, right? And explains a lot of the math behind it as well as their experimental setup and everything that they generate within this. And then so going over the paper, to me, it's like the paper is very in depth, right? But what they do is very self explanatory to me. And it's easier to explain it just by looking at it. And so, to me up front, this solution it's an elegant solution. It's not a solution that I would have thought of for this individual problem. And I've spent a lot of time researching this problem because it's a known problem. And once you dive into the math of these things, it's very apparent where there's math problems, like where the math problems lie, and like things that you can do or try to do to fix these math problems. And then this solution is counterintuitive to what I would do to try to fix this math solution. So I think like in a million years, if I was just doing this on my own, I would never come up with this solution. So it's interesting, right? And then that's how these things happen. It's a very simple, elegant solution, but I would never think of it in a million years for this particular problem. And the reason is so the problem that we're trying to tackle overall with the attention mechanism is that the attention mechanism is it's very not mathematically efficient. It's inefficient as could be, right? And then so we want to make it more efficient. And then how they make it more efficient is very straightforward. They add an additional matrix layer to it. And then so I would just never think that I would never come up with that concept initially, right? So, okay, our challenge is to make this matrix more efficient, this matrix array more efficient. So how we're going to do that is we're going to add an additional matrix layer, and that additional matrix layer is going to end up helping us to make this more efficient, and it does. And so looking through kind of what we're looking at here. So I've created a class and it's called Selective Attention. And for most of this, this is very straightforward. This is all attention, right? And then so up until here, this is all just the standard attention mechanism, all of this, right? And so if I was to build a standard attention mechanism, this is exactly what I would utilize. It's utilizing linear regression and then as well as softmax scaling in this instance. So it's utilizing like rounding and adjustment. So we're doing some as much as we can in this instance as far as performance wise to increase the performance. And then we've got our forward and our backward propagation. And then we create our forward loop. And then now let's introduce the F matrix for selective attention. So very straightforward. What we're doing is so we take our attention matrix, our normal attention matrix, and then we add this F matrix, this F layer. And then the F layer, it tells the model what to subtract. So that's what makes it interesting, right? And then so it trains, and then so as the model trains, it figures out what tokens are necessary in its training and what tokens are not necessary within its training. And then let's say it's training on a ham or spam data set. Is this ham or is it spam? And then so what it will do is it will go through and it will classify ham or spam, and then it'll find out it's, let's say it's a 1 billion parameter model. And then this F matrix will update and it'll find out, hey, out of our 1 billion parameters, there's 200 million parameters that are never utilized throughout this process. This specific process, we never utilize these 200 million parameters. So, and moving forward, and in all future instances of this process, which is extremely important, ignore all those whole 200 million parameters. Just don't include them in the equation anymore because we don't need them. And that's all that this does, right? And then so it's very straightforward. It's rarely so it's doing back propagation, and that's how it's doing it. It's back propagating itself, and then the weights to ignore, right? And then that's all that happens, and then it outputs its projection, and then its output is ignore these weights. And then so this is essentially, oh man, uh, from here to here is the this is the matrix. It's just the additional. It's an additional matrix layer that you're adding. So you're adding a layer, but the layer is telling the model what parameters to subtract from the equation. So adding complexity to reduce complexity. Brilliant and easy, simple solution, right? But it's that like that first that adding the complexity. I would just never think to do that. And so, I mean, good job, Google, right? Cool. I like it. I dig it. It works. Very simple and straightforward to me to understand. I understand exactly what it works, what you're doing here, what exactly is going on. This is super cool to me. The F matrix is amazing. I dig it. Congratulations. Like this is a cool concept. I dig the F matrix. And so if you like this type of content, please like and subscribe. Thank you very much.